Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's lesson, we will be learning about what are ratios. So let's get started with the following problem. At the local candy shop, jelly beans are sold for $6.50 for 3 pounds. At this rate, how much should 10.5 pounds of jelly bean cost? So how do we solve this problem? Well, what we can do here, set up something called a proportion that is consisting of ratios. So let's do that. So here we can write that 650 over 3 is equal to x over 10.5. And obviously we can include the units here as well. And here we can say that $6.50 over 3 pounds is equal to x over 10.5 pounds, where x is actually the cost of 10.5 pounds of jelly beans. And as a matter of fact, if we keep it this way and do the dimension analysis as well, we should end up with dollars. So how do we solve this? What do we do next? Well, the next step is to simply cross multiply here. So here we obtain $6.50 times 10.5 pounds is equal to 3 pounds times x. And as you can actually see here, we can easily cancel out the pounds on both sides, right? Because we can divide pounds on both sides and we're actually just left with dollars, and that's perfect because x is indeed in dollars. So again, 3 times x is now $68.25. Therefore, we divide by 3, we obtain an answer of x equal to $22.75. So what does that mean? It means that 10.5 pounds of jelly beans cost $22.75, and that is the answer. Now, when we translated this word problem mathematically, we were able to set up something called a proportion. And as a matter of fact, in today's lesson, we are going to learn what proportions and ratios are and how do we apply those in geometry. So let's first get started with the definition of proportion. So a proportion is a comparison between two equivalent ratios. For example, A over B equals to C over D. Or we can just simply write A to B is equal to C to D using columns here, as you can see. But what are ratios? A ratio is a comparison between some number, usually 2, quantity. And the example is, for example, A over B or A to B, again using colon, or just simply written out as A to B. Now, if we go back to the previous example here that we had, we did set up a proportion, and this proportion compared two different ratios. The first ratio being $6.50 over 3 pounds, and the second ratio being x over 10.5 pounds. So what did we do afterwards? Well, afterwards, we cross multiply to solve the problem. But how do we know that we can cross multiply? Or in simple words, how do we know that this is always true? What mathematical justification is there that allows us to cross multiply a proportion? Well, let's discuss that and get into the proof. So let's say we're given A over B is equal to C over D. We just simply cross multiply and we obtain that AD is equal to BC. But how do we know this? How do we know that this is always true? How do we prove it? Well, the first thing you want to do is to get started with the given and also think about, once we have the given, what can we do on both sides of this equation? Well, as you can see, we can, for example, multiply by b on both sides, because then the b's would cancel on the left side of the equation. Basically, we can say that b times a over b is equal to c over d times b, but then as you can see, the b's would cancel, and we're left with a is equal to bc over d. Similarly, we can now multiply d on both sides, and what do we notice here? We notice that the d's simply cancel out because d over d is simply 1. So we're left with the following equation, that AD is equal to BC. And there you go, is the proof. So it was a very simple two-step proof in which we multiply b on both sides, and then d, and we can prove it. Now, the fact that we just proven this means that there is a theorem that justifies this step. So the theorem that justifies this is the product of the means is equal to the product of the extremes. Again, every time we prove something, we can now develop a theorem. But what are the means and what are the extremes? Well, in this particular example, the means are simply the b and the c values, or as you can see on the right side of this figure, the means are the numbers that are closest to each other when you write them as colons here, as shown. And the extremes are the ones that are the furthest apart, written with colon. So now that we have this theorem, we can now simply use this theorem when we have to justify the cross multiplication. Again, if we go back here, this proportion, once we set it up, we cross multiply, and the reason for that step should be the product of the means is equal to the product of the extremes. Let's now look at an example. How do we find the value of x here? Well, we have a proportion, 4 over x is equal to x over 9. What do we do first? Well, first we cross multiply, and we obtain that x squared is equal to 36 because the product of the means is equal to the product of the extremes. Then we take the square root on both sides, and we obtain that x is equal to plus minus 6, or we end up with the absolute value of x is equal to 6. So there's actually a meaning to this particular example. So when we end up with an unknown variable squared, and then we have to take the square root of that, that is called the geometric mean or the mean proportional. So let me define that first. The mean proportional, or the geometric mean, of two numbers a and b is the number x that satisfies a over x equals to x over b. Then we can simply write that x squared is equal to a times b because of the fact that the product of the means is equal to the product of the extremes, and then we can simply take the principal square root of a times b. So that is actually defined as a geometric mean and has many applications in geometry. But what is the meaning of the geometric mean? What significance does it have? Well, we can simply compare it to the arithmetic mean. And once we compare it, we can get an idea on what that actually means. So let's say we want to find the arithmetic mean between 4 and 9 as supposed the geometric mean. So we all know that the arithmetic mean is simply the average between the numbers. In this case, since we have two numbers, we're taking the average between 4 and 9, and we do end up with an average of 6.5. So what's the meaning of that number? What does 6.5 mean? Well, it's simply the distance between 4 and 9, which is equal. As you can see here, we have a number line, and if we, for example, drew in the distance here, or calculated the distance from 4 to 6.5, that is 2.5, correct? And if we take 6.5 and go 2.5 units to the right, we also end up with 9, okay? So both of these distances are congruent, or they're equal in measure. So we can think of the arithmetic mean as a one-dimensional problem, okay? How about the geometric mean? So the geometric mean between two numbers, you end up with the square, okay? For example, if we look at x squared is equal to 36 here, what comes to mind here? Well, we can think of an actual square. So let's say we have a rectangle where the dimensions are 4 and 9 as shown in the figure. Basically, these are the two numbers a and b, the 4 and the 9. What are we doing here with the geometric mean? We're basically trying to find a shape which is a square that has the same exact area as this rectangle with 4 and 9. And as you can see here, the square would have dimensions of 6 by 6. And these are the sides, okay? So as you can see, it's a two-dimensional problem, the geometric mean. It's like taking a rectangle and trying to make a square out of it, okay? So that's how you can visualize it. So we are going to learn many applications in geometry, particularly with right triangle. Let's look at an example now. If the arithmetic mean between two numbers is 12.5 and their geometric mean is 12, then what are the values of these two numbers? So let's set up the equations first for the arithmetic mean and the geometric mean in terms of a and b. So for the arithmetic mean, we simply write 12.5 is equal to a plus b over 2, which is basically the average of these two numbers a and b. Now we can just simply multiply by 2 to obtain that 25 is equal to a plus b. So there's not much we can do at this point other than expressing the equation for the geometric mean. So here we have a over 12 is equal to 12 over b for the geometric mean, which means that AB is equal to 144. So at this point, we have two equations and two unknowns, and we can definitely solve for this problem. Well, a simple way to proceed here is solve for a in the first equation, that a is equal to 25 minus b. Once we solve for a, we just substitute it into the second equation to obtain that 25 minus b, that quantity times b, is equal to 144. That becomes 25b minus b squared is equal to 144. And we end up with a quadratic equation in the form of b squared minus 25b plus 144 is equal to 0. Now let's factor this. We want to think of two numbers that add up to negative 25 and multiply to 144. So here we end up with b minus 16 quantity times b minus 9. That quantity is equal to 0, which means that b could have two different values. That b could equal to 16 or b can equal to 9. Now regardless, if b is equal to 16, then the a value is 9. And if b is equal to 9, then the a value is equal to 16. Does it matter which one is b, if it's 16 or 9? It doesn't really matter, because in the example, here we're being asked, okay, which one are these two numbers? And the two numbers are simply 9 and 16. So what does that mean now that we have the answer, 9 and 16? It means that if we take the average between 9 and 16, the linear average or the one-dimensional average, we obtain a value of 12.5. But if we take the two-dimensional, so to speak, average or the geometric mean between 9 and 16 is 12. And that's basically how you solve these types of problems. Okay, so that's basically it for today's lesson. I hope you enjoyed it. Thank you for watching and have a wonderful day.